Okay. Hey, everybody, this morning. Um, I hope you have to make a little effort. I know everybody has been hanging out with the Scotland-Switzerland game yesterday night, and you have a few more talks to go this morning. So please be awakened. And second point, I'm sorry, it looks like the red lamp is gone. So look on the lateral screens if you don't see some stuff I try to explain to you. So, okay, the topic here is, as you said, it's going to give you a glimpse at some results which have been obtained by the Chang'e-4 mission. And just to remind you, it's a joint effort which has been done between the National Astronomical Observatory of China and my institute in Toulouse, so IRAP. So just to refresh your mind about this, the Chang'e-4 mission is a mission which has been which has landed in South Pole Icon in January 2019. And on the left, you can see the white star, which shows you the landing site, which is about 370 kilometers away from the very center of South Pole Icon. And it's in one of the lowest parts of South Pole Icon, as you see with the topographic profile below. So what I'm going to address has to do with spectral observations which have been obtained by the Venice spectrometer on board the rover U2. And that is what you see on the right here. So this spectrometer makes measurements in two parts, a Venice and a SWIR part. The Venice part is a camera, a CMOS camera, and the SWIR part is one single detector, which is in the red circle that you hardly see, which is slightly on the left of the white screen here. And the integrated result is one spectrum that we can obtain on the surface of something like a few square centimeters at the surface of the moon. So then, since I don't want to be too long, I will have to skip here, but just to give you a flavor of what I'm going to implement here has to do with an advanced way of applying the modified Gaussian model deconvolution to complex spectra. And that's a work I've been working for several years in a row. So if you're interested, check the literature. I just give you a flavor here. The idea is just you are able to do a systematic search for all the mafic minerals, considering a different number of Gaussian functions to go from simple mineralogies, that is to say, just considering one mineral, either pyroxene, orthopyroxene, clinopyroxene, or olivine, or a mix, up to a complex situation in terms of mineral assemblies where you consider the three minerals together. That's on the right. And the number of bands will vary from 5 Gaussians to 9 Gaussians, depending on the situation. And this approach has already been implemented in the past to a number of targets, mainly on Mars, but also on the moon. Some stuff I published a few years ago about Copernicus in particular. So you can go back to this if you want, publish in LPSC or so, or even also at ELS, and also implemented on lab work, being tested on a very complete olivine solution suite of samples, ranging from firelite to a forsterite, to be able to derive as precisely as possible the Mg or forsterite number. And so today, the idea is to implement this approach on these Chang'e-4 in situ spectra acquired in South Pole Icon along the traverse. And the traverse has been now running for 5 years, as I said, that is to say more than 60 lunar days. And here the data I'm going to show you are focused on the first 41 lunar days. So here is a selection of the spectra I'm going to discuss with you here. And the key on the right of the code is a little complex. The only thing you need to know is that number 3 means the third lunar day after landing, and 41 means the 41 lunar day after the landing and the start of the operations on the moon. So I'm going to give you a flavor of a few targets which have been monitored and documented. And the focus here is mainly on rocky targets. So, but some of them, as you will see, the first 2 are within the red circle that I hope you see this time here. That's where we get the integrated spectrum, we have a mix of rock and soils, and on the next one, we'll have only rocks. And for each of these targets, I applied the MGM deconvolution I described to you. And for each of these targets, the best solutions among all the possible solutions I tested was systematically a mix of orthoclinopyroxene, clinopyroxenes, and olivine. And I give you an example here, but you have a few more, just to give you an idea of how this runs. Oh, we don't see much again. So you get a spectrum in the log diagram. It's a log reflectance diagram. And again, this is a combination of a continuum. It's a second order polynomial continuum, which is mixed with the Gaussians to describe the absorption features. And the results is quite good here, but not perfect. The RMS is around 0.6. And you can see on the upper part of the graph at the bottom here that you have a straight line zigzagging, which is shifted with respect to the 0. That gives you the flavor of the RMS value all along the spectral domain. Ideally, it should be all flat, but we have some little wiggles, but it's quite a good modeling anyway. So here is another target. So again, that's Lunar day 3. You see another example. I will not comment all of this because I will wrap up otherwise the results. But you can see the characteristics in terms of band center and depth of absorption and width. One more here. So you see now that is Lunar day 26. This time target is only rocky. There is no soil component, so to speak, or regolith component in the red circle. So it's only a spectrum acquired on a rocky surface. And you get also all the ideas of the solutions with the Gaussians here. One more on the Lunar day 26. The same, this one now on Lunar day 27, again, a rocky surface. Lunar day 41, so on a big piece of rock here. And you see still that the RMS are still quite good. It's around 0.04. It's kind of very flat along all the spectrum. That means that the modeling you can rely on the modeling here. And last one here, okay, on another part of the rock. So now if I summarize all of these results, and instead of putting you a list of numbers and tables, I captured all the band centers that they have been producing with this deconvolution, and they end up in the two ovals or shapes that you get here, the ellipses. On the what I call the Adams diagram, you know, the pyroxene diagram, the 1 versus 2 micron band absorption features for the band center. You see that for the red part, it corresponds to the low calcium pyroxene or orthopyroxene characteristics, and they are very grouped in this red oval. For the high calcium pyroxene, it's in the green part, and that's where we land, you know, slightly on the right of the 2.1 micron band. If I replot this in the quadrilaterals of, you know, pyroxene quadrilaterals, with on the left side the Hazen et al. Solution 1978, on the right it's Clutis and Gaffey 1991. You see where the ellipses land in this diagram, and you see that it's more or less in the Ojite field. You know, well, I should say that quadrilateral, on left you have the diopside, on the right Edinburghite, ferrocelite at the bottom right, and enstatite on the left. So this is also something I could not develop much here, but we are able to characterize the FO MG number. And for all the spectra I showed you very quickly, they basically all fall in the range of the blue box you see here. So around this F phosphorine number 0.6, 0.7. So from all of this work, if you use the absorption depth or the Gaussian band depth that you get for the different minerals that I characterize, you can get an idea of the relative mafic mineral proportions. And that's what I show you here. And I've been considering two cases, either the 105 micron olivine band, that's the upper line each time that you see in the table, and the lower line has been derived from the 1.25 micron band depth. So I will not comment too much because of lack of time, but for the central part, the green box, if you see the green, there is a real consistency within 2% in the relative mineral proportions, whatever you consider either the 105 or the 1.25 micron absorption depth. And it tells you that the dominant mineral is the clinopyroxene here, but then you get orthopyroxene and olivine with a rather almost equal weight. And all of this is kind of balanced close to 1/3 for each, but clinopyroxene being a bit higher. The possibility exists, as you see at the bottom here, that for some rocks, we get some plagioclase contribution, which may disturb the olivine proportion. And I say so, because when you look at the results from the 1.25 micron band, it looks like you would be apparently more olivine, which may not be the case. It may have to do with the presence of plagioclase. So here, that's where I will stop. The preliminary interpretation and current implications so far are that the rock mineralogy appears to be driven by a mix of augite and olivine, basically hyalosiderite. It's FO number 6070 and plus enstatite. It's in general agreement with the results previously published by some of our Chinese colleagues. However, it doesn't exclude the occurrence of plagioclase as well. That's what I list here. And what I wish to highlight here, and unfortunately it's in red, so you cannot read it, or from here it's very difficult. The olivine proportion in the rocks seems to be higher than what was found so far in the regolithic soils. So, of course, what is really important now to establish is the origin of these rocks is still to be determined. They are kind of rare along the traverse, but that's what would be of high interest. And of course, the acquisition of new rocks, new rocky targets as the traverse continues would be of very high importance and relevance, of course, for testing the various hypotheses that I'm sure you are all scratching your heads about, and so do I, for the interpretation. Is it related to an impact melt differentiation effect across South Polaitian? Are we dealing with some kind of local volcanic resurfacing event? Are we dealing with distant impact ejecta boulders? All of this is possible, and I don't have the answer. The only little point I will make here is that likely the results which are being obtained recently in situ and the characterizations of the sample to be written by Chang'e-6 very soon, in 1 week from now, if everything goes well, might help also understanding more about South Polaitian. Thank you.
Thank you for the presentation. Any question? We have one there.
Hi, Patrick. The regolith observed with the U22 rover was interpreted to be Vincent ejecta, if I'm not mistaken. Would you then use your analysis to exclude the same origin of the boulders as the regolith, or you have any additional thoughts on that?
No, thank you. I mean, that is a possibility, no problem. The Vincent crater ejecta could be part of the game. What I'm just puzzled is that I don't find so many boulders to my taste. I would have expected to see a lot more boulders across the traverse. I didn't mention that, but within the last 5 years, the traverse has already represented a path of 2 kilometers, basically, and not so many rocks were found. So it's kind of very scattered and very dispersed. And from that, it's difficult to make a judgment whether or not you're dealing with the same ejecta or kind of scattered stuff. That's what I will say.
Hi, Patrick. Abby Freeman from JPL. I'm curious if you've had a chance to do any comparison with any of the orbital spectral data sets, if there's any regions or areas that have similar spectral signatures that might be a clue.
You mean from the Chinese data or in general? No.
Any of the data sets that exist, like the N-cube
No,
data?
I didn't check so much about this because I was really curious of what we could get in situ this time. I know the global work has been done a number of times, I think, by a number of people. But you're right, I didn't so far cross-check what we found very locally, very in situ. And again, as you know, Abby, it's orbital stuff is great. I've been doing this half of my life, roughly. But usually you're dealing in this case with something which is representative of a large expanse of surface, that is to say regolith. And here I'm much more curious about the potential petrology of the rocky surfaces I can find. So there could be some discrepancies. It's quite possible as well between the orbital results and the in situ rock petrology or rock mineralogy that we're characterizing now. And that was the focus here. Okay. So I guess, it's always a long way from the cup to the lips. And we have only a little bit more information now, but trying to explore what is a Luna incognita. And we're making little progress. I hope we will, in the end, get to something with South Polycon, as you know, it's such an exciting place.
Time for one quick question.
Jeff Gillis Davis, Washington University. Do they take spectra of boulders in more than one place so we can see variability? Or is it just one spectra per rock?
Thank you. I should have, well, I tried to explain it too, but it's, no, it has been acquired along the traverse. And so these have been taken on separate rocks. And among the little selection I just showed you, there are a few places where you have several spectra acquired on the same rock, but you have also spectra acquired separately on diverse boulders, or let's say kind of outcrops. So I've made here a selection of 7 spectra out of maybe 20 or 25, which were acquired in different locations and different pieces of rocks. But that was the point here. There is some kind of commonalities in terms of the presence of the mafic minerals I detected, because I tested all the other solutions, and I know people are excited about norites, for instance. If there were just pure norites, in principle, my procedure should have found a better solution just looking at olivine and orthopyroxenes. And the results I got were not so good. So that means that there was still a missing component. And the best I can say so far is what I told you, you needed the clinopyroxene.